So we have ideas to insight. So here's the definition of insight, and I like this. It says the ability to perceive clearly or deeply, penetration. Okay, and my mission is all about penetration because we're looking all the way down to the core of Mars, and so I really like that. And a sudden understanding as a complex situation or problem. We're really looking at some really complex problems. So my own definition of insight, and here we've uppercased the I and the S, that's the way we do it. So when you put those two capitals in there, it turns into this interior exploration using seismic investigations, geodesy, and heat transport. Took me about 2 or 3 weeks to come up with this acronym. I really liked InSight and had to have something that worked together with what we do. And that's one of the things we do at NASA. We sit around for weeks and weeks and weeks trying to think of acronyms that really work. But the other reason why I like InSight is because it really talks about, it's really seeing inside, and this mission is all about seeing inside the planet. And we've gone to Mars more than a dozen times to the surface. We've gone lots of times in orbit. We've explored the bejesus out of Mars, but we've never penetrated below the very thinnest skin of Mars. What we've explored is kind of like a fraction of 1% of the planet. And what this mission is supposed to do is kind of right that sort of long-standing hole in our understanding to really get the other 99.9% of the planet. So the whole story of this mission starts back in about 1977. And in case you don't know, it turns out that the best way to look at the inside of a planet is by using seismology. That's really the gold standard of exploring beneath the surface of a planet. And this was well understood way back in the 60s. In fact, the first instrument, it turns out, that was ever sent to the surface of another planet was a seismometer, and not in the Apollo missions. It was actually in Ranger 3 through 6. They had seismometers on the Rangers that were supposed to crash on the planet, and they had shock-absorbing balsa wood things that were supposed to do it. And all those things missed the planet, which was too bad, but they did put seismometers on Apollo, and a lot of what we know about the inside of the moon comes from seismometers. And then the first mission to land on Mars had seismometers with it. It was a Viking mission, 1977. I was in grad school, and as a geophysicist, had high hopes for this. This is the abstract from the paper that came out of that mission. It was a long paper, and they went on and on about they did this and they did that and the other thing, and we didn't really see anything. So it was a big disappointment. And there's reasons why, and I'll get into those a little bit later. And so I'm coming along about 5 years later, and finally out of grad school, and I sort of published what was then my magnum opus about the stresses and strains on the surface of Mars that you can get from the topography and gravity and some geology. And there's this one little irritation. You know, I'm doing all this analysis, and I was kind of a code monkey / geologist, which is kind of a weird mutant hybrid if you think about it. But I was sitting in my office, the door closed, I'm working on my computer, and it's the thickness of the crust was a crucial parameter in all these calculations. I had this huge model and all this fancy gravity measurement and topography measurement and everything. But the thickness of the crust sort of went into it, and I just had to make up a number. I make up 50 kilometers, fine, 50 kilometers. But it really irked me. And I thought, we really need to get the thickness of the crust and do a seismology experiment on Mars. And that should be sort of a lesson to you. Sometimes you get an idea, and it can derail your entire career, which is what it did for me. So this mission was 35 years in the making. You'll say, so we had Viking in 1977, and it had a seismometer on it. Seismometer failed, so you go back and do it again, right? And so there's a big space from 77 to the late 80s where we didn't do anything in space due to a lot of politics, but we started going again kind of in the late 80s. And so these are kind of the missions that NASA and ESA, the European Space Agency, were working on during that time. And so they had some that were sort of mission studies in red. Mars 96, that was a Soviet mission, which turned into a Russian mission, which actually was launched. It got about 1,200 kilometers towards Mars before it turned around and came back. So that had seismometers on it, but it didn't really help us much. This measure network was a NASA Phase A study. Actually, it was an approved mission that went on for several years. I was the pre-project scientist on that. Intermars, these all happened. We were going great through the 90s, and then in 96, it all kind of came to an end. I like to say that this is this measure network is the only mission that we know that was destroyed by a meteorite. And those of you who know about Alan Hill's 84001 might know what I'm talking about. It's an inside joke. They thought there was biology on it. Some people still do. And so everything except for life on Mars came to a screeching halt. So it didn't really work out. And over the next 10, 15 years, there were a whole lot of proposals. And unfortunately, every single line on this chart is something that I was involved in. And these proposals are big deals. They take about a year to do. And then you go on and they don't get chosen. And so you go, forget this. And then somebody says, well, there's another proposal opportunity coming up. This is actually a really diabolical thing that NASA's done with the planetary program. So all these guys at the beginning, these are all agency-decided missions. They have a bunch of people sitting at NASA headquarters and say, well, we're going to do this and we're going to do that. And they make a mission and they ship a bunch of money to JPL and then they change their mind. Then they said, well, we're doing all the work here. Why don't we just say, let's do a competition and have all the scientists kind of duke it out and see which one mission wins, and then they'll do all the work, and then we can just kind of choose one at the end. And so all these proposals, you go in, these impact proposals, it's a discovery program. There's about 30 proposals that go into NASA. You spend a year of your life, and they pick one, and you keep on doing this, and pretty soon you think, well, what are the odds here? I mean, maybe I should be playing the lottery instead. So by that time, I was kind of committed to it. We're going through the 2000s, and these things just keep on getting shot down. But there's an evolution we're going through here. These ones down here on the left, these are 12, 16, even 20 landers all at once doing seismology. And if you know anything about seismology, you like to have lots of stations. You can triangulate things and do stuff. By the end here, Netlander, that's 4 stations. And then we're trying to figure out Cerberus, that's 4 stations. Well, maybe what we ought to be doing is trying to make this a little bit more affordable. And so there's an evolution of how you're approaching it. It's the execution. It's the same idea. We're trying to improve the execution here. And finally, we've got InSight that was selected in 2012. Again, from a set of 26, I finally rolled the dice and got it right. Or maybe I got a good idea. Okay, so what's InSight all about? InSight is all about understanding the formation of terrestrial planets, and that's all the rocky planets. And by looking at the interior structure and process of Mars, and we do that using seismology, mostly, and then geodesy, which is the study of the dynamics of the planet, and heat flow, which tell you something about the energy sources in the planet. And the way that we can do that by looking at Mars is by recognizing that all the rocky planets share the same basic structure. They've got a metallic core, they've got a dense rocky mantle, and they have a less dense rocky crust. And sort of the proportions of these things change among the planets, but presumably they're all formed by the same processes. We know a lot about the Earth. We've got good information about what the Earth's made out of, what the size of the various different divisions are in the Earth. But the Earth is kind of a special case. Okay, we've got one situation, we've got one case. You really can't draw very many conclusions from a single data point. And plus, Earth is kind of a problem because plate tectonics has sort of taken everything and stirred it up. And so if we really want to understand the stuff that happened at the very beginning of the formation of the planet, Earth isn't a very good place because it's gotten all erased. Mars, on the other hand, is a really good place to study this stuff because we have evidence, we have isotopic evidence and other kinds of geological evidence that suggests that Mars really hasn't changed much in a bulk sense since the first 100 million years of its existence, which on a planet's lifetime is barely getting out of the cradle. And so if we can go to Mars and find out what the size of these various divisions are and their basic compositions, we can then go back and look at our models of formation to see how they really work. Okay, so the sort of the bare bones of how things work is how planets form. We start forming through accretion of meteoritic material. We've got all this kind of dust that's swirling around that has the composition basically of a carbonaceous chondrite, starts clumping together. As it gets bigger, it begins to heat up, both from the sort of the kinetic energy of the stuff falling in, and also from radioactive elements that are in there. It begins to heat up and melt. Then stuff happens, and you end up with a planet. Okay? It's not real satisfying, but that's what InSight's supposed to address right here. And the interesting thing about it is a carbonaceous chondrite is a very specific rock. Okay, it's a rock that has a very specific composition, has certain minerals in it, and if a geologist would pick up a chondrite off the ground, it looks like a rock, but he could look at this and say, this is a meteorite, and the whole Earth was made out of this stuff, but no rock on Earth, no rock that didn't actually fall from the sky recently, has the composition of a carbonaceous chondrite, and the reason is because of something called differentiation. And the differentiation we understand in terms of the lunar magma ocean model. This is something that we actually figured out mostly by looking at the geochemistry of rocks we brought back from the moon, together with the Apollo seismic information, which told us about sort of the internal structure. And what happens is when this thing accretes, it heats up and it melts either completely or maybe the outer half of it melts. Anyway, once it's all molten, there's a lot of weird and interesting chemistry and physics that goes on. I mean, the first thing that happens is that the metals condense into little droplets, and since they're about 2 to 3 times as dense as a silicate, they rain down to the center to form the core. Now, there's still lots of iron left in this planet, but it's iron oxide. So the amount of stuff that actually goes down to the core depends on the oxidation reduction state of that melt, which is something that is fixed by the way that things accrete. And so the actual composition of that core tells us a whole lot about the state of this melt at the very beginning and how it was put together, how it cooled, and what the sort of details of the chemistry of this melt are. It also, as these things kind of rain down, they can absorb some other elements. For example, they can absorb sulfur, they can absorb calcium, even carbon, and pull that down into the mantle, and that'll be a key thing later on. So as the thing cools, then the silicate mantle starts to crystallize. It starts to freeze out, basically, and it freezes out in a very complex way. If you kept it stirred up, and you kept it stirred up as it cooled, when you got to the very end, you'd have a giant carbonaceous chondrite again, minus some of the metal. But you're not stirring it up because what happens is you got lots of gravity, and heavy things sink. And in particular, as this thing cools, you get things. These minerals, olivine, pyroxene, that crystallize, and then they kind of rain down and form a mantle from the bottom. As these things are crystallizing out, it's changing the composition of that red stuff that's left. So it's pulling out some elements preferentially, and it rains down, and now the stuff that's left has a different composition. And in fact, you go to the next step here, as it starts squeezing up, you start crystallizing out lighter things that actually float up to the top and form a crust. And so you end up with a planet with a crust, a mantle, and a core. And the details of these chemical reactions, the sort of the physical chemistry of all this is really complex. It's difficult to simulate in the laboratory because these are at billions of atmosphere pressure, which is a hard thing to get in the laboratory. So what we want to do is get some information about the actual composition of the planet so we can go back and take our models and start refining our models of how this process works. Once we have that, then we can extrapolate it to other planets and even exoplanets that we're getting with some of the astrophysics that we're doing today. Okay, so in terms of our mission, I can look at this thing down here. I'm trying to look at this sideways, and it's really tough. So our mission is really close to the Phoenix mission of 2007. We use almost the same lander with some updated electronics. We launch in March from Banerdt in a very fast trajectory because we're on a bigger rocket that we need because NASA doesn't make little rockets anymore. We land in September of 2016. We have about 2 months of deployment phase, 2 years, which is 1 Mars year on the surface, and then we have an end of mission in 2018. So first thing to notice is that that's really, really close to now. That's 14 months, 26 days, 18 hours, and 3 minutes from now, in case you're counting, but who's counting, right? The other cool thing about it is that usually you launch from Florida, you have to deal with the alligators, but we're actually launching from California, so we get the sea otters instead of the alligators, which are a lot cuter. And the reason we can do this is because since we're launching on an Atlas, which is the smallest rocket that we can use, it actually has about twice the throw capacity that we need. So we don't have to launch from Florida in that eastward trajectory to take advantage of the Earth's rotation. We can just launch south over the ocean and just sort of muscle our way into orbit. And that saves all us guys in Pasadena from having to get on a plane so often. Okay, so here's a mission animation for InSight showing our rocket actually. This is a Phoenix animation. We didn't do our animation yet. One of the ways we got this mission through is by reusing a lot of the Phoenix stuff and including a lot of their PR materials. So just pretend like instead of a Phoenix logo there, it's an InSight logo. Okay, so anyway, so we're launching on a rocket. Doesn't look a lot like this rocket, but a rocket's a rocket, right? So we're launching to Mars. We go up, and then we have a 6.5 month cruise to Mars. So here we are 6 months later, we get close to Mars, we have a cruise stage there that's taking us to Mars, that gets ejected, and then we enter the atmosphere the same way that manned space capsules do with an ablative shield, which slows us down in the upper atmosphere. Once we slow down on that to about 2.5 to 3 times the speed of sound, we pop a special parachute, which takes us most of the way down to the planet. As we're going down, we get to a certain altitude, we can acquire the surface. Once we acquire the surface, after we get rid of the heat shield, we can start figuring out what our altitude is. And once we know our altitude, we get to about 4 kilometers. Oops, we drop, and then we fire our rockets. No airbags bouncing around, no sky crane. It lands on a set of rockets just as God intended a good lander to do. Right? Okay, so once we're down, now we have to start deploying things. We have some really cool solar arrays they're sort of like a Chinese fan. They unfold like that. Actually takes about a half an hour to open those things up. And then we're ready to go. And from then on, it is really Phoenix stuff, which we're not interested in. So the first thing we have to do is find a place on the planet to land. And usually for a Mars mission, finding a landing spot is a really complicated scientific process where you get 30 scientists in a room and they beat each other over the head with things until they finally, one guy's standing and says, we're going to land here in my favorite geological spot. But for my mission, we're interested in the core. It doesn't matter where we land on the planet. You can land anywhere on the planet. It's just fine with me. So we go for the flattest, safest, most boring location that we can think of. Something like this would be very bad for our lander. It's very rough and stuff. I actually took this picture in Hawaii. It used to be a nice street in a town somewhere. Not a good place to land. So we actually were able to sort of limit the amount of area on Mars that we could land on to this region here. And that's actually one of the only places we could land because of the altitude constraint of our lander. Tells us we can't land in the southern hemisphere because all that orange stuff is really high. If you try to land too high, you just don't have enough air between you and the ground to slow you down. And you can't land too far north because then your solar panels don't give you enough electricity in the wintertime. And so this is just kind of the Goldilocks region for Mars for us. And it turns out we have a lot of company here. We're only about 300 kilometers from Curiosity. We're in the same general region as Spirit, Viking 2, and the wreckage of Beagle 2. And so that's where we're landing. We've already started taking some pictures. These are the safe ellipses in this region. An ellipse is kind of the dispersion of places that you might land because there's atmospheric variations and stuff like that deflect your trajectory a little bit. And last summer, we were able to narrow it down to sort of 4 ellipses up in the upper corner of that. So that whole area, each of those ellipses is about 100 kilometers long. So we've got about a 250 by 250 kilometers square that we're narrowing it down to, and next year we'll pick a single one of those ellipses and we'll plaster it with high resolution images. Right now, with the assets we have at Mars, we can cover that entire ellipse with photography that gets down to about a half-meter resolution, which tells us if there's any boulders at all. And my geologist friends already tell me that this is the most boring place that I could possibly land. Some of them aren't even talking to me anymore. Okay, so here's our lander. Like I said, it looks a lot like the Phoenix lander, except the stuff on the deck is a little bit different. We have different instruments. And these are our major instruments. The one over there on the right is our seismometer. It's covered, you can't really see the seismometer because it's covered by a dome. That protects it from the wind and stuff. The one on the left is called HPQ, that stands for Heat Flow and Physical Properties Probe. And what that does is it gets the heat flow coming out of the planet. This long string coming down there is a cable that has thermal sensors along it, so we can get the thermal gradient. The mole down there is what's pulled it down, and that has a heater in it that gets the thermal conductivity. So between the two, we can get the amount of heat coming out of the planet. And then we have an arm, which deployed those things, and a camera so we can see what we're doing. And those two kind of cone-shaped things on the edges are our medium gain antennas that we use to do communication with the Earth, to do our precision tracking. I'm going to talk about all these a little bit more. And then we have a bunch of other kind of auxiliary sensors. We've got anemometers, we've got a pressure sensor, a magnetometer, and another camera. So, talk a little bit about the seismometer. First of all, to sort of get us on the same page as what we're looking at, a seismometer is basically a mass on a string. And if you shake the ground up and down, you accelerate the ground, the mass sort of stays still because the spring accommodates the motion. You can measure that x, the distance between you and the ground, and its variation, and that's your measurement. You can see the shaking of seismic waves. So we're measuring with a device that'll have a noise floor of 10 to the minus 9 meters per second per root hertz. Okay, and that's pretty good for a seismometer. A really good research seismometer is about 10 times better than that. But just to give you an idea, that's roughly half the radius of a hydrogen atom. Okay, so that's the kind of measurements that we're making there. And you can imagine that kind of, if you have something sort of kind of sitting out in the ground somewhere, the wind's going by, things are happening, it's really hard to make that measurement. And so most of the time on the Earth, we put these things in a basement or a mine or something like that to try to get it really quiet. We're just sticking this thing out in the surface, so we have to do a lot of extra stuff to kind of make it work well. So this is our actual instrument. It's a little bit more complicated than just a block sitting on a spring. The thing up in the upper left-hand corner is the basic sensor, and then we stuff 3 of them into an evacuated container in order to get our 3 axes of measurement. And as I said, a seismometer measures almost everything in the world better than it measures seismic waves. And so we have to measure all these other things in order to be able to sort of take that out of the data. For example, pressure, just sort of a little gust of wind coming through, it actually increases the pressure a little bit. It pushes the ground down, lets it back up again. That's a signal. It looks like a seismic signal, so we have to measure the pressure. The same for magnetometer. The magnetic field, even though we have this thing shielded, the magnetic field moves things a little bit, and so on. So we have all these other little sensors. We don't call them instruments because if you tell NASA you're flying an instrument, they think that's a big deal. So these are sort of stealth instruments that will actually get science out of these things, but don't tell my sponsor yet. Okay, so I think one of the key ideas that allowed this mission to go forward is going from the sort of the paradigm of multiple stations and triangulation to saying, well, can we get all this information from a single seismic station on Mars? And the way that it turns out you can do that, we could have done that back in the 90s if we thought about it, but there are a lot of analysis techniques that you can use to get information about the interior of the planet from one seismometer. I'm not going to go into these. Almost every one of the charts in this presentation is another half-hour presentation, but suffice it to say that, one of the things that we did in our proposal that we hadn't really done before is really go into the literature, really, get into the seismic community and pull out all the stuff that's been figured out over the last, mostly the last 20 years in pulling out interior planetary structure from one seismometer. And you don't use that much on the Earth, but there's been so many PhDs going through looking at this stuff that there are a lot of these techniques out here, and we're confident that we can do the job. The other question, of course, is since we've never seen a Marsquake, do you actually have them? And we've done some analyses. We can see faults on Mars, so we know there were earthquakes at some point. You can actually look at some dating through time and figure out what you think they should be. And if you sort of just draw a line kind of between the Earth and the Moon, you get a number that tells us we should see something like 100 Marsquakes per over the life of our mission. But even if we don't get Marsquakes, we have actually a couple of guaranteed sources. One is the Phobos tide. Phobos is pretty small, but every time it goes over, it actually induces a solid tide in Mars, which is about 5 millimeters or so, and that happens every 7 hours. And that's really hard to detect because it goes really slow because it takes 7 hours to go up and down. But if you do that for a whole year and you keep on sort of accumulating that data and accumulating it and beating down the noise, you can actually get the size of that tide. And the amount of that tide depends on the size of the core, because if you have, especially if you have a liquid core, it'll go more than if you have a solid core, which is harder to deform. And so that's one thing. Another thing are meteorite impacts. We can actually know that there's meteorite impacts on Mars. We've seen them happen with before and after pictures, and we know to within about a factor of 5 or so what the rate of meteorite impacts, and we should see a couple of dozen of these. And finally, the atmosphere. I talked to you about how the pressure pushes the ground up and down. Well, how that propagates through the planet again tells you something about how the structure of the planet is, so we can get something from that. Okay, then we have the heat flow experiment. We have this mole, which is a mechanical thing. It actually can't see too much here. I had a movie, but it has a German codec that apparently isn't on their computer here. But basically, we wind up a spring and releases a hammer that knocks it down, and then we have this tether with a bunch of temperature sensors in it. Okay, and this isn't the final presentation, but that's okay. Okay, so that goes down, as I said, about 5 meters and gives us the thermal gradient and the heat flow from the planet. And finally, the other major experiment is this tracking experiment. It turns out that with the deep space networks and there our X-band tracking, we can get the position of our spacecraft in inertial space with respect to quasars out to the distance at the kind of 10 centimeter level, about 4 inch 8-inch level or so. And by doing that, since we're attached to the surface of the planet, as the planet rotates, we can actually look at the variation of rotation of the planet as a function of time. And this allows us to measure the precession, which is sort of the wobbling of the top, and nutations, which is sort of the interaction between the fluid core and the solid outer part, which are directly tied to the properties of the core. And so in the same way that you can tell whether an egg is hard-boiled or raw, we can use the same kind of analysis with a little bit more sophistication to not only find out whether the core is liquid or solid, but actually get into what the density and what the size of the core is as well through this moment of inertia. And this goes on and on and on, and finally, after a while, there you can see the liquid core, and you can see that the pole is wobbling differently, and we should be able to pick up the wobble of that core, which is only a few tens of meters of wobble, but we should be able to get it with our measurements. Okay, and sort of the last aspect of this, the other thing that was really critical in putting together this particular mission is surface deployment. So we get all the way to Mars, we've gone 650 million kilometers, we land on the planet, and the seismometer is still a meter from the surface, which is what we want. There's a seismometer on Viking, this is Viking 1 back in 1977. There's the ground. What's wrong with this picture? Those should be the same place. Brilliant idea, let's put them in the same place and actually make the measurement. That's, by the way, why they didn't see anything on Viking. What that long, 15-page article basically said was that the seismometer turns out to be a really good wind sensor. Every time there's a wind gust, they saw lots of stuff, but that's about it. Okay, so the way we do this is with a robotic arm, We've got an arm that we actually inherited from a mission that never flew in 2001. It'll pick up our seismometer off the deck and place it on the ground. We've got cameras that take pictures of that whole work area so we can make sure we don't put it down on a rock. And once we've let go of that seismometer, it has a thermal shield around it, but it's exposed to the wind, right? The other thing that is kind of interesting is you can see a little loop in the tether behind the seismometer there, and that's necessary in order to decouple any motions of the tether from the seismometer, because just the expansion and contraction of that tether was going to put way too much noise in. So once we're done with that, we've dropped all the tether to get rid of all the tension. We go back and pick up the wind and thermal shield. And one kind of cool thing about this is it actually has, as you pick it up, you can see it has a skirt. It turns out that not only, the seismometer is sensitive enough that if you put a butterfly on top and it flapped its wings, you could see that in your seismic signal. So we designed something to keep the butterflies off. And as it's keeping the butterflies off, it actually seals against the wind as well. And it has about 4 different layers of material there, including some chainmail. It's similar to what the knights of yore used, and it accommodates all kinds of fluctuations in the ground. And once we're done with that, we can go back and pick up our heat flow probe. Again, this doesn't do us much good unless it's on the ground. So we pick it up. Both these things have these pretty complex cables attached to them that have a lot of different signals going back and forth. And that management of those cables is one of our biggest challenges on this mission. And once we get it down, we can do our science. By the way, this 2-minute video takes about, like I said, 2 months on Mars, because since we don't have people there and we can't joystick it because the one-way light time's about anywhere from 10 to 25 minutes, this all has to be done autonomously, and robots are really, really slow. Okay, and just a little bit of status. This was a picture that was taken about 2 or 3 weeks ago. We're actually starting to put our spacecraft together. The different pieces are kind of laid out here on the floor at Lockheed Martin. I was there last week to see my baby, and it's looking really, really pretty. And here's our instrument on the test floor in Toulouse. The seismometer is actually being built in France, and the heat flow probe is being built at DLR in Berlin. And so that's one of the other ways that we actually save money. And fortunately for us, those are actually the best instruments for the job as well. So those are the different pieces of the seismometer. And so I'd like to close with a quote from Albert Einstein, which has sort of a double meaning here in terms of looking deep into nature. This is a picture that was taken by Spirit and Gusev crater, where you can actually see Earth in the sunset. And if you don't believe Albert Einstein, Chinese fortune cookie's never wrong. So thanks for your attention.